Here we are going to take a look at one geometric curve which we find in our everyday life in the most unusual of places. And there is also a very uncanny coincidence related to that. So let us start by our first situation here. Say you are having a candlelight dinner, and this could be your cup of coffee or maybe glass of wine, and here is a candle, a source of light. Now as the rays from this source of light are incident on the interior of the glass or the cup, then they get reflected. So I have shown the reflected rays in red, and this set of reflected rays form a pattern. So it creates an impression of a heart. If you want to see how this happens ray by ray, we can do that here. So this is the inside of the glass and this is our source of light, and we are looking at this single incident ray, say striking here, then here, here, and like that. As it does so, it leaves in the interior of glass a certain space, a certain shape where it doesn't enter, and thereby it creates an impression of a curve, an envelope, okay, which is shaped like a heart. Now let us go to an altogether different scenario. So this time we have got a ring, and there is a little diamond fitted on it, and it is sitting around your finger, shown here in cross section. And because this ring is loose, it is kind of rolling on your finger like this. Then every point on this ring traces an interesting curve. So let us say this tip of the diamond, okay, is going to trace that curve, and let's see what happens there. And voila, again it is a heart shape. So isn't it uncanny that we see a heart-shaped curve in our glass at a candlelight dinner, and the ring on our finger, a point on a ring on our finger traces the same curve, and it is shaped like a heart. No wonder it is called a cardioid. Let us now go to the geometry, the mathematics behind this curve, and we'll focus on the equation of this curve, say the polar equation. So we will start with this radius here, r, which is increasing and then decreasing again slowly it will increase and decrease, and in fact that's what its equation says. This is the equation of a cardioid, which is r, the polar coordinate, equal to some constant capital R multiplied by 1 plus cosine theta, and this cosine function, the cos function, is assigning the periodicity to this radius. You can see this bracket over here will vary between 2, 1 plus 1, and 0, 1 minus 1, as theta varies from 0 to 360. Now let us see the family cardioids hail from and some of its interesting cousins. For that we are going to generalize this equation of a cardioid by using two constants instead of the single constant capital R, and that gives us this equation: R is equal to A plus B cos theta, where A and B are arbitrary constants. And depending on their relative sizes, we get a different family of curves called as Limacons. When A is equal to B, we get a special case called as cardioid, and I have color coded it. So A is equal to B is in green, so that is this green curve, the cardioid. When A is less than B, then the negative value of the cosine function will not be compensated by it, and therefore R will become negative, and it will go deeper inside, forming a loop like this. When A is greater than B, then R will never become 0. It will always remain positive. So instead of getting a deeper cusp like this as in a cardioid, we will get a shallow dimple, something like this. And finally, when A is equal to 0, we will get a circle. And this is the same circle that supported the rolling circle around it. So it plays the role of your finger in the rolling ring analogy. And finally, let us see the kinematic definition of a limacon with a loop. So here is our fixed circle. Around that there is another circle that we are going to place, and instead of taking a point on its periphery, we'll be taking a point inside, and the curve traced by that point is a limacon with a loop. So this is how a limacon with loop gets formed.